Hi guys, so these are the worked solutions for paper 2 of your end of year exams. It's got a different front cover because I just printed off a fresh copy because I couldn't find one of the ones you did, but trust me, it's the same questions. As with the other video, please do not watch this entire video from end to end. It is long and not particularly exciting. Just skip through to the questions that are most relevant to you. So as we take a look through at this first one, it tells us about Elise, who wants to investigate the length of time that people spend in her library on a particular day, and she wants to know whether the variable t, time in minutes, is discrete or continuous. Remember, our way of judging that is, can it only take particular values, or is it counted? In that case, it would be discrete, or can it take all values in a range, including all the little decimal values, or is it measured? And in that case, it would be continuous. And if we think about time, do we count it or do we measure it? It makes much more sense to measure time. And so that means time is continuous. It then says that she collects her data by sitting at the front desk and asking people as they walk by if they would like to answer her survey. What type of sampling method is that? That sounds to me like convenience sampling. Remember, convenience sampling is a biased sampling method, and it doesn't involve randomly selecting people, but just going by like whoever says they're willing to do it. So this here is convenience sampling. Right. Her data for 160 people visiting the library is shown in this table here, with the time in minutes up here and the frequency below, and it asks us to find the value of k. So if these are our frequencies, they should add up to 160, our total number of people. So that's how we're going to find our value of k if we do 160 minus 50 minus 62 minus 14 and minus 8. Then we find that k is equal to 26. The next thing it asks us to do is to find the modal class. The modal class is like the mode. It's just that it's described as a modal class when we have these groups here rather than single values. I'm really sorry, I can just see the lines going down. It's going to get really dark in here. Can I find my clipper? No. Oh well, I think it'll get dark and then hopefully it will get light again, but fingers crossed you can still see. So the mode of these classes is the most common one, the one with the highest frequency. We know now that k is 26. So the one with the highest frequency is this one. And when it talks about the modal class, it's asking you to write out that entire thing there. So 20 less than or equal to t less than 40. And then it says, write down the mid-interval value for this class, as in what's the value halfway through that class, which is 30. I think it's relatively obvious, but if you're not sure, you can add 20 and 40 together and divide it by 2. I am so sorry, it's getting so dark. It's almost closed and then it'll open back up again. It then asks us to use her data to estimate the mean time that people spent in the library. For a grouped frequency table like this one, oh God, I really hope the blinds open. Yay, there we go. I think, yeah, they're just opening now. Hopefully you can see better again. So for a grouped frequency table, we actually have to take the mid-interval value of each group and use that to use our calculator to calculate the mean. So that's kind of what it's setting you up for here. It's trying to get you in the headspace of that. So our mid-interval here is 10, 30, 50, 70, and 90. So that is the information we're going to put into the spreadsheet part of our calculator. I'll just write T for time here and F for frequency here. So 10, 30, 50, 70, 90, and then we put in our frequencies 50, 62, 26, 14 and 8. And then a reminder, how do we find the mean? We can go to statistics, stat calculations. This is one variable statistic because my top tip for you is that frequency is not a variable. So one variable statistics, even though there's two lists there, there is only one list of data. The other one is frequency. My X list is T for time. Oh. My frequency list was F. And then after that, I just hit OK. And as I take a look through there, my mean of X, that's what that symbol represents, is 33.5. Then it says, using the table, write down the maximum possible number of people who spent 35 or less minutes in the library on that day. So if we take a look at where is 35 or less here, these ones are definitely 35 or less. And these ones here, well, it's everything between 20 and 40, but they could all be 35 or less, right? We don't know exactly where they fall between 20 and 30. And so if we're talking about the maximum possible number of people who spent less than 35 minutes in the library, it could be all of those 62. So that's what we're going to add on. But then all of these values definitely cannot be 35 minutes or less, so we don't include them. And when I add that together, I get 112. Great. The next thing we're going to move on to is she assumes her data is representative of future visitors, and then find the probability a visitor spends at least 60 minutes in the library. So that means the lowest amount of time they can spend in the library is 60 minutes or more. So we're interested then in these two categories here from 60 and above. I had some people add on this 26, but this isn't including at least 60 minutes. Look, it's not got the extra equal sign there, and it's just between 40 and 60 minutes. So I'm going to do 14 plus 8 is how many spent at least 60 minutes out of a total of 160 people. So that there is my probability. And I can just leave that as 22 over 160. That's fine. You'll get all your marks for that. Or we can type in 22 divided by 160 and get the answer 11 over 80 as well. Or the decimal answer, it doesn't matter. This isn't formatted very well, but it says the following box and whisker diagram shows the times in minutes that the 160 visitors spent in the library. So this box and whisker plot here shows that same data we've been talking about. And it asks us for the median time spent in the library, which is this value here is the median on a box plot, which is 26. It then asks us to find the interquartile range, which is going to be our upper quartile minus our lower quartile. So call that lower quartile. So our upper quartile is 50 minus our lower quartile of 16, which is 34. And then it says, hence, show that the longest time that a person spent in the library is not an outlier. So the longest time somebody spent in the library is 92. So what we're going to do is our outlier calculation, and we're going to check, is that value above or below our boundary for an outlier on the top end. And as a reminder, that calculation is Q3 plus 1.5 times the interquartile range. Oh, I don't know what I'm doing there. Interquartile range. So that's going to be 50 plus 1.5 times 34. Escape. 50 plus 1.5 times 34, which is 101. Now, if you do that and you have the value of 101, you'd have 2 out of 3 marks. But it does say, show that the longest time the person spent in the library is not an outlier. So that needs, I'll just write it down here, it needs an extra sentence, which is, which is above our maximum time of 92. Good. The next thing it says is that Elise believes the box and whisker diagram indicates that the times spent in the library are not normally distributed. Identify one feature of the box and whisker diagram which might support Elise's belief. Now, this is a question that's checking your understanding of a normal distribution, and something we know about normal distributions is that they are symmetrical, right? They're evenly balanced across it. And when I look across this box and whisker diagram, it is not symmetrical. So for me, I think that's the obvious answer here. The box and whisker diagram is not symmetrical. Great. Okay, let's move on to question number 2. This is about the admissions team at a new university. They're trying to predict the number of student applications they'll receive each year. And it says the number of years that the university has been open is N. The admissions team collect the following data, and it wants the percentage increase in applications from the first year to the second year. To find a percentage increase, we need to find the increase, but then work it out of the total of the first year. So it's going to be 12669 minus 12300 to find the difference, divided by the total in the first year, because we want the increase from the first year, and then times by 100 to make it a percentage. So let's spin the fraction first. 12669 minus 12300 divided by 12300, which is then a 3% increase. It then says it's assumed that the number of students that apply to the university each year will follow a geometric sequence. Write down the common ratio of the sequence. There's 2 ways to do this. One is if we know it's a 3% increase, you might just already know that the answer is 1.03 as our common ratio. Or if you're not sure, you can do U2 divided by U1, which will also give you 1.03. So this number divided by this number. It then asks us to find an expression for UN. So that's basically saying, what is the formula for UN? It's a geometric sequence. We know that UN is U1 times R to the power of N minus 1. I had a few people just leave it like this, but we do need to know the actual expression for this sequence. So that's going to be my U1, my first term, 12300, times 1.03 to the power of N minus 1. Good. It then asks you to find the number of student applications the university expects to receive when N equals 11. So that one's nice and easy. We're just going to type in 12300 times 1.03, 11 minus 1. Which gives us 16530. I'm not going to put in that 0.2 because it asks us to give our answer to the nearest integer, which is the nearest whole number. It then asks us to find the total number of students who applied to the university in the first 7 years. As soon as I see the word total, I'm thinking about the sum of a sequence in the first 7 years. So we're looking for S7 of this geometric sequence. Our formula for Sn is this. And so that's what I'm going to fill in, 12300. And And that's then what I'm going to type into my calculator. My answer to that is 94248. Either that or it does say express your answer to the nearest integer, so just left like that. Great. It then says in the first year there were 10,380 places at the university available for applicants. So we're now onto something new. Just to be clear, this is how many people were applying, and now it's telling us about how many places there were available. So there were this many places available initially, and then the admissions team announced that it will increase by 600 every year. And it asks us to find an expression then for that sequence. Now we've got to be very careful here because this is now no longer a geometric sequence. It's just increasing by a fixed amount every year, which makes it an arithmetic sequence. So I'm going to write out the arithmetic sequence formula. And that's what we're going to fill in for our expression here. So U1, 10380 plus n minus 1 times 600. You can simplify it if you want to, but you don't need to. It says for the first 10 years that the university is open, all places are filled. So all of these places are filled for the first 10 years. Students who receive a place each pay an $80 acceptance fee and calculate the total amount of acceptance fees in the first 10 years. So again, that word total tells us it's going to be the sum of a sequence. So we're now looking for S10 of this arithmetic sequence, which has this formula. And then if we fill that in, so it's going to be 10 over 2, 2 times, I can't remember, 10,380. And the common difference was 600. There we go. So that's what I'm going to type into my calculator very carefully. I think there's a problem with my 8 key. There we go. Okay, just make sure you know it's got the plus in there, the brackets are all in the right place. That's all important. Otherwise, you will not get the right answer. But the right answer for the sum of the first 10 terms of the sequence, I'm actually just going to put this up here. Can you see that okay? Oh, let me shift down a little bit. There we go. Is 130,800. So that's how many places were filled in the first 10 years. But then we know each of those places generated $80 in acceptance fees. So we're going to multiply that by 80 to find the total amount, which is, I'm not going to try and say this number. Perfect. There we go. And now it gets on to a really interesting question. So when n equals k, the number of places available will for the first time exceed the number of students applying, and we want to find the value of k. So essentially, we've got this formula for the number of students applying, we've got this formula for the number of places available, and we want to know when they first cross over, so when the number of places available will swap over and be higher than the number of students applying. My advice would be this: we can either end solve or we can graph it. Let's end solve first, because I think that's the most obvious thing that you would do. But as we move on to the next question, graphing it might be more helpful, but we don't know that yet. So let's just end solve it. Remember, if we want to know when does it exceed it, we're really interested in that place where they cross over, and the place where they cross over is when they are equal to each other. So I'm going to take those two sequences that I had in the first part of my question, so this one here and this one here, and we're going to put them equal to each other. So 12300 times 1.03 to the power of n minus 1 is equal to 10380 plus n minus 1 times 600. Let's see what we get when we end solve. I haven't actually tried this out yet, but hopefully it gives us a sensible answer. If not, we'll deal with it in a moment. So and then comma n, so that we find that. Good, there we go. So that has given us a sensible looking answer of n being equal to 12.49. I do think we probably need to round that yet to the nearest whole number, because we're talking about the value in a sequence. And if that's the crossing over point, then before it hasn't exceeded it yet, and afterwards it has. So we need our n to equal 13. Perfect. Then it says, from this point forward, so from that value of 13, state whether after n is equal to 13, the university will always have places available for all applicants. Justify your answer. Now this is, this is a question that's stretching into making sure you really understand. But just to be clear, we had an arithmetic sequence, one that forms a straight line, which was the number of places available. And we had let me get this right. So it was something like this, I would say. This is our geometric sequence, which represents the number of applicants. And this is the bit where you need the understanding. An arithmetic sequence does form a straight line. A geometric sequence does form something curved like an exponential function. And what we found was originally there were more applicants than places. Then at this point, 12.49, suddenly the places available was more than the applicants. But if we think about the nature of a linear function and an exponential function, it makes sense that they have a second place where they cross over. Now, you could have done that all on your understanding of linear and exponential functions, or potentially what you could have done is graphed this with an x in it, graphed this with an x in it, and if you'd have zoomed out far enough, you also would have been able to see those 2 points as well and seen that it does cross back over again too. Okay, right, let's move on to our final question, which is about a scientist who's conducting an experiment on the growth of a certain species of bacteria, and the population is P and can be modelled by a particular function. This should definitely have been on the same page, but I think it was for you. So what I'm going to do here is, we know P is the population, so I'm going to add that in. And this is one whole thing. It is the population. And T is the number of hours since the experiment began. It then asks us to write down the value of P of 0, as in when the time is 0, what is the value? Now this is a little bit complicated, right? Because we have a value of 0 here, but we don't know what k is. But the good news is anything to the power of 0 is equal to 1. So even if we don't know what that is, we know that this entire thing is equal to 1, because what we're doing is 1,200 times k to the power of 0, which is 1,200 times 1, which is 1,200. It then says interpret what this value means in context. And in the context, so what we're saying is the time is 0, and this is the population of the bacteria. So you could either say the starting population of the bacteria or the initial population of the bacteria. Either of those would be fine. This next question I would like to apologise for. I added it in because I wanted to have a question that involved understanding an inverse function, but I shouldn't have put it in here because we didn't know the value of k yet, so it wasn't possible to solve it kind of in this order that I put it in. I had a few people who tried it out or figured out k first and then put it back in. But what I decided to do is just remove those 2 marks from the exam. So instead of it being out of 53, it was out of 51 instead. And I apologise for not double checking my order there. I just fancy putting in something inversely, but it was definitely in the wrong place. So let's skip that one. And it says 3 hours after the experiment began, the population of the bacteria was this. So 3 hours later, that's the population, and we want to find the value of k. So I'm going to fill that into this here. So my population is 18750 is equal to 1200 times k to the power of 3. Because my time is being measured in hours. Some people put it into minutes, but no need. And then we're going to end solve that. There we go. So we've got k is equal to 2.5. And then it says, find the population of the bacteria 1 hour and 30 minutes after the experiment began. So now we're trying to find P when we know T, and now we know K as well. I had a few people call this 1.3 or 90, as in 90 minutes. But the time is being measured in hours, and 1 hour and 30 minutes is 1.5 hours, right? 30 minutes is half an hour. So as I put that in, I'm trying to find the population. I'm trying to find the population, which is 1,200 times 2.5 to the power of 1.5. And as we've got everything filled in here, we don't need to end solve. We can just type it in. If you did end solve, it's not a problem, but do watch out. Call P just the letter P. Do not put P of T, this bit with the brackets, into your calculator because it will assume that P is being multiplied by T instead. Okay, moving on. It then says that the scientist conducts a second experiment with a different species of bacteria, and the population of the bacteria is modelled below, and T is still time in hours since both experiments began, and it wants to find the value of T when both populations are equal. So when is this population going to equal this population? And we can do that by putting those two equations equal to each other. Let's try and end solve that. I'm not sure what answer we're going to get. yeah, that seems to give us a sensible answer. So our answer there is t is equal to, 3.43. Good. It then says it takes 2 hours and m minutes for the number of bacteria in the second experiment to reach 19,000. And it wants us to find the value of m, giving our answer as an integer value. For now, let's just find out when this equals 19,000, and then we'll deal with the rest of the question later. So we're going to end solve 19,000 is equal to 5,000 times 1.65 to the power of t. Which gives us an answer of t is equal to 2.66587. So there is our 2 hours, and this is a decimal version of the number of minutes, but it would like m in minutes, and to convert from a decimal to a number of minutes, we can just do that decimal multiplied by 60. So I'm going to minus off 2 there so that I've just got that decimal, and times it by 60, and I get this value here, which if I round that to if I give my answer as an integer value, is going to be 40 minutes. Okay, the final question on the entire paper is this one here, where it says the bacteria in the second experiment are growing inside a container. The scientist models the volume of each bacterium to be this big. So essentially, the size of each bacteria is this, and this is how big the container is. And it wants to know how long would it take it to fill the container. So there's a few different ways to do this. Remember, this is the formula for the population, but so that's how many bacteria there are. This is how big each bacteria is, and this is how much space we have. I think there's a few different ways to do it, so my way isn't the only way, but I would suggest we take the population formula, we multiply it by the size of each bacteria, and that will give us like a formula for how much space the bacteria take up, right? If that's how many and how big each one is. So if we do 5,000 times 1 point, could you just, I'm really sorry, Toby, I'm just recording a video right now for something. Sorry. Sorry about that, guys. I just had a parent getting a little tour around, but I don't want to pause the video. So we're going to do 5,000 times 1.65 to the power of t, multiplied by the size of each bacteria. And we want to know, when will all of those bacteria be as big as our container? So we can put that into NSolve. 5,000 times 1.65 to the power of t, there we go, times oh my goodness, what am I doing, guys? Right, times 1 times 10 to the power of minus 18 is equal to 2.1 times 10 to the power of minus 5, and we are trying to find t. There we go. So we've got t is equal to 44.2, to 3 significant figures. Perfect, and that is the end of the paper.